Welcome back to the second part of the Module 3 webinar for Euclid, where in particular we're going to talk about the tools that can be used to help publish and to help create your data set. So to start with, I want to talk about an open source framework called Sekine, which is a registry for data sets. Okay? So it allows data publishers to say, here's my data set, to describe it, and then allow third parties to have a look at that through a void view, through an API view, to have search over the top of them, so to find the data sets that are useful to them. Here's how Sekine looks out of the box. So we have a representation for each data set and a nice set of tools for looking through them. All of the things that were just described, the different kinds of metadata, are represented there in HTML for a human user or in an API or in RDF. A particular big installation of this open source tool for managing data sets is the DataHub. Okay, so the DataHub, among other things, is actually the source of the big linking open data cloud that you see very often. Indeed, there are more than 5,000 data sets there. You can also create groups of those things to help understanding and to help communication and interaction. So the front page of the DataHub looks like this. The most obvious thing is the text search box. Okay? So if you're interested in information about postcodes, about police information, about music, you can have a keyword-based search in here, and it will start drilling down to the relevant data sets that you can explore. As I said, part of what's registered through this Sekine at datahub.io is all of the data sets that are eligible for inclusion in the linking open data cloud. Okay? So that's not just having provided some kind of RDF in some kind of data set. There are criteria for inclusion in that cloud that mean that it's both linked and that it's open. Okay? So what's the degree of interlinkage and what is the license that the data is available under are among the criteria for inclusion in the cloud diagram. The cloud itself is an open data set, so you can investigate that, and you can also see the links on to the data sets that are included or whose metadata is included in making that data set. So here is a representation of that cloud. It keeps getting bigger, keeps getting denser. The best way to understand it now is by the color coding down in the bottom right-hand side that says, for instance, this nice tranche down the cloud is the life sciences data. Okay, everything with that color. Just to reiterate what we have said before, the arrows in this diagram, or the bubbles in this diagram, are entire data sets. Okay? The arrows between them are interlinkage. So if you point at a data set, you use some of its instances in describing some of its resources in describing your resources. And it's worthwhile pointing out just how very dense in linked open data the use of interlinkage to DBpedia is. Growing also the links to Freebase, especially because now that has this commercial character in being the publicly accessible part of the Google Knowledge Graph. So the criteria to get into that diagram, well, you have to publish your data according to the principles. So as was described in the first half of this webinar, it must be of a decent size, which means at least 1,000 triples, though many of these run through millions into, like Freebase, billion. It must contain at least 50 RDF links to another data set already in the diagram. So if it's made completely in isolation without any interlinkage, it's not eligible to go in the diagram. Then finally, access must be provided, open access in fact. There must be some license that says that this data can be at least consumed and usually reproduced. So when it comes to the use of search technology in general, we'll talk about this more in the next module, but there's two interactions with linked data. One is using linked data to enhance search for documents, especially web search. Okay? The other is the provision of a search interface to help you find data or vocabularies about data. So we're going to provide some information about both of those and then go into more detail in the next module. When it comes to enhancing search that already exists, there are now some very big success stories for what the emerging generic term is structured data, okay, but in which linked data, especially RDFA, plays a big part. So if you publish your content on the web using RDFA, so putting RDF into your HTML, you'll find advantages from the search engines like Google and Bing. You'll also find advantages in the social world now, for instance at Facebook. So we'll give a quick idea of those. Now here at Google, so Google's early experiments with this were called rich snippets. They're now rebranded structured data, Google structured data. Okay? And this means by putting RDFA or other means to express this into your HTML, your search results on Google can be as pretty as these are. Okay? It means instead of just having the blue link with the title page, the green link, and the black first paragraph or first sentence, first two sentences, you start to be able to add information that makes your search result look more attractive. So most notably the bitmap, but also the average review represented here, and some classifications, some here cooking times and calorie ratings for food. You see also at IMDb, the music database, you see another example with the star rating. Okay? So this has been a big driver both sides. It's been a driver for search engine optimizers to say this really increases your inbound traffic, which are quantified by several people in this space using linked data. And it's also a driver for linked data people to get more of their linked data into their content as it's been crawled by the search engines. Okay? So as I say, rich snippets, now called structured data, was a main driver for that, but now by far it's not the only game in town. With rich snippets, they have, as the name snippet might suggest, Google have chosen certain vocabularies and said, we will explicitly, as we're crawling the web, scrape that stuff out of your HTML. Okay? And RDFA is a good route to doing that. So if you go to their structured data testing tool, formerly called the rich snippets testing tool, and put in a URI for a page, it will tell you all of the data that it pulls out of that page from RDFA, like this. Okay? Worth mentioning also, I don't have a picture for you, but Google Webmaster Analytics, if you register your whole site, so if you prove that you're the owner of a site, it will show across your whole site what structured data it's extracted, for instance, from RDFA. Now, rather than cherry-picking vocabularies like this and being dependent on community maintenance of those vocabularies, what Google did next, in combination with Microsoft and Yahoo, was said, we're going to publish for you a vocabulary which we'll be looking for. Okay? So we'll give you canonical but high-level terms for the kind of things that we're interested in and want to represent. And that vocabulary is called schema.org. Okay? It's recognized by Bing and Google, Yahoo and Yandex and others, and aims to a shallow depth, cover a broad number of domains. Okay? It doesn't attempt to tell you, stop making ontologies, we'll do it all. Instead it says, we'll make a shallow ontology that you can align yours to. And when your RDFA, when the stuff you put out on the web, is expressed in this, aligned to this vocabulary, to schema.org, then the search engines will pick it up and know what to do with it. So if you visit schema.org, you'll see the top-level hierarchy of the things that are covered so far. It's worth mentioning again, so we would quote Dan Brickley, working at Google, saying that they're looking for a balance between defining to the right depth for them to know they have a standard representation of some things, but also at extensibility. Okay? So in some cases, you might really use schema.org as an internal representation, knowing that you can extend beyond there. In other cases, you might choose to use a different vocabulary, but then project out, and we've seen several ways to do that, inference and construct queries, into the schema.org vocabulary as you put your content out onto the web. The aim is also not to define everything themselves in the schema.org working group, but to reach out to communities who are doing vocabulary definition and include their things in schema.org. So an early success story there was RNews. News providers have been working under the IPTC for a long time to make a vocabulary for news-oriented metadata, which is somewhat richer and more specific than the generic things in Dublin Core. RNews was about to launch when schema.org did launch. Okay? So instead of putting out a separate vocabulary, they instead worked with schema.org for a few months and integrated the top level, the abstract stuff, into schema.org. So you'll see creative work, and you'll see a lot of properties for that in the core schema.org vocabulary, and the rest of RNews sits as an extension. More recent, but worth mentioning, technology released from Google is the use of the knowledge graph. Okay? So the knowledge graph builds on Freebase to have information about those things that you're doing text search for. Okay? So to pick back up our running Beatles example, if you type in Beatles, you'll see what's called a disambiguation pane. At the top right-hand side, there'll be a photo of the Beatles and a bunch of information underneath them that comes from Freebase and from Wikipedia pulled through from Freebase interlinkage. Similarly, if you search for one of the albums, so here we said Beatles Let It Be, you'll see the disambiguation pane is the album cover, the Wikipedia paragraph about it, Freebase or Wikipedia structured metadata, and even the inclusion of the track list on that album. Okay? So the Google interface is using graph-like data via Freebase to produce this kind of search experience. Okay? They're also giving away the public part, which is Freebase, in the form of RDF, so we can build these systems ourselves and interlink with Freebase. You can't quite see how disambiguation works on this slide, but take another example. If you search for Mona Lisa on Google, the disambiguation pane at the top right will show you La Joconde, this picture by Leonardo. You see the picture, and the structured information that's come from Freebase underneath says it was produced in an earlier century, it was produced by Da Vinci, etc., etc. It's housed at the Louvre. Underneath that, you'll see there's another representation of Mona Lisa, your text search term, which is the 1990s Hollywood movie called Mona Lisa. Okay? If you click on that one to disambiguate instead of the picture to the movie, then obviously the data will change. It will show you the cover of the movie, when it was made, who the director was, etc. And the search terms that you get will change, okay, to match this disambiguation of what you're actually looking for. If it thinks you're looking for the painting, it tells you a lot about the painting. If you tell it you're looking for the movie, the search terms will be about the movie instead. So Freebase, which is used to drive that, an earlier acquisition by Google, is a large structured knowledge graph. Much like Wikipedia, the aim is that people can go in and edit there in a wiki-like way, but it's oriented to data. It's not oriented towards narrative text like Wikipedia. So, an announcement while we've been busy preparing this material for Euclid is that Bing are now doing a very similar thing, okay? Bringing together data in a large knowledge graph. Even more bragging rights on the Microsoft side with Bing. The graph database where they store all of this data to drive their knowledge graph is itself somewhat compliant with RDF and with Sparkle. That's the Trinity database. So now you search for leopard on Bing, you get this disambiguation and lots of structured data from their graph to help your search. They've gone even further into, for instance, using the graph where it concerns biology to show you things like subspecies across there, so you can explore through the data and then only at second hop go to web sources for it. Okay, and then the third big player, Facebook. Facebook for a long time have been trying to build a graph that extends on their core value. Okay, their core value, they have a very big graph of users, more than 500 million users, and they have social relationships between them. When they saw that building relationships with non-person things in their graph was catching on, you would go and like a certain car or like a certain movie on Facebook, they decided to extend that beyond the realms of their social network onto the web. So if you had any product or event, you could put a like button on your page and it would be included in their graph. Okay? So you could go back and say, who likes my stuff? What else did they like of mine? What else did they like of the competition? And for instance, how do we target them in advertising? The means to get your page into Facebook are by putting RDFA again on your page. Okay? You use the RDFA to say this is a page about this kind of thing, okay, with these kind of characteristics. Please make associations between my car or sporting event or movie and people who've liked them. Okay? Facebook also have the possibility that you can ask for the part of the open graph that you're allowed to, which is mostly the graph around you as a Facebook user, in the form of RDF. So you can ask, please tell me in Turtle all of those things that I've liked. Okay? Everyone I know, everything I've listened to on Spotify, everything I've watched on Netflix, and all of these external products that I've liked. So it forms a graph like this. I'm a friend of this person, I'm a friend of this person, I've listened to this track on Spotify, I've cooked this recipe on Epicurious, and I've watched this thing on Netflix. Okay? All graph-oriented information, all available, subject to access rights in RDF, and very useful for some purposes. I'm going to skip a few slides on that and talk very quickly about their new use of this, which isn't just selling it to marketers, it's also making your search experience, so to come back to search, richer. Okay? From your Facebook profile, you can now ask quite sophisticated questions like music liked by me and my friends who live in and some geographical area. Okay, so our slide preparer found, logging into her account, that I, for instance, like Sigur Rós and Radiohead. Interesting. There are some constraints so far over that search, but it's a really nice application of what building such a graph, where RDFA is one technology to do, where RDF in general is one technology to do so, can yield in this search area. Okay, so we're going to move on in the next 40 minutes to talk about tools to produce data from other sources, and then about interlinking the data that's produced. So the first tool that I want to talk about also springs from Google via MetaWeb, who made Freebase, and is called Refine. Refine fits into our diagram mostly in terms of these three tasks, mapping, interlinking, cleansing from these kind of sources. Comma-separated values and tab-separated values, open ways to represent spreadsheet information, proprietary spreadsheets, so it will deal with Microsoft Excel, HTML tables, and JSON also to a degree. So, for instance, if we have such a table over on the right-hand side, whether it's represented in HTML, where it's quite readable, we have a table of artists, starting with, as always here, the Beatles, country of origin, period active, when they're first charted, and their total certified units. Okay? So this table has some rich information about sales here, which we don't get from MusicBrainz. That's what it would look like in HTML, which we could extract. Equally likely is that we just get that core information in a CSV file. Okay? So we're going to show the process of turning that into RDF to augment the MusicBrainz data set that we have. So OpenRefine looks as follows. The first thing we can do is create a project and bring in some data, either from the web, from a file, or actually enter the data ourselves. When we do so, what we're aiming to do is turn this CSV into this nice, well-formatted RDF. Okay? In order to get from there to there, you should notice some common things that are necessary with this kind of data. The first thing is the column A, the first column, is just text strings, just labels. Okay? So the Beatles, Elvis Presley, just the text label. On the right-hand side, we have numeric data, okay, but it's not purely numeric. We're really writing down million, for instance, here. Okay? If you compare that to the RDF, much more specific, we use shared identifiers from MusicBrainz for the artist. Okay? So these are ambiguous. You might find more than one Queen. Okay? Here, we say exactly which one we mean with the URI. We're unambiguous about what the relationship is. Okay? What this data is saying, well, we actually use a predicate that can be looked up to say we're dealing with the total sales information. Okay? And then instead of this mixed numbers and letters representation of the sales, we really reduce that down to a number in standard format with a data type tag to say how it should be interpreted. Okay, so the first thing we need to do is to look at the columns, identify which ones we're interested in, and which ones are going to be the means to raise a triple with a given subject, and which ones are just giving information to that resource. So they're triples through a certain relation, they're objects through a certain relationship. To get there, first we might do a bit of transformation on the data. So we have a language called grel, which strangely, even though everything is open now, still has the G in front. Okay? But it's a regular expression language that lets us, for instance, say, okay, where we see million, that means we're going to take the other column. First it says, let's split these things. So we use the space between them to say there's two different tokens here. So we produce a column 2.2 and 2.3 here. Okay? And then we use 2.3 to say, if that's million, it means multiply by a million. Put 6 zeros on the end. Okay? So when we produce a new column, total sales through that rule, we've split these things, we've used million as a multiplier, and we've produced the actual numerical information that we want in the RDF. The question is, how are we going to make that RDF? Well, the first thing is, at this point, we install an extension to OpenRefine to be RDF aware, one that was developed at Derry in Ireland. And it will let us nominate an ontology, which is the basis of our classes and properties. Okay? It will also do what's called reconciliation, which is this turning labels into URIs, either by the built-in reconciliation that what the tool originally called Freebase Refine has, or by using other data sets over their Sparkle endpoints. So we can use the Sparkle endpoint for MusicBrainz, made available by the Euclid project, to do the lookup. If you've got a resource labeled The Beatles, what is a candidate URI for that? Okay, so when we do the reconciliation part, that's exactly, as I said, where you take The Beatles and Elvis Presley and turn them into URIs in MusicBrainz. Okay? So now we've got the subjects we're interested in, proper URI identified resources, and the objects we're represented in, proper numerical values. So now we get to do this thing called edit RDF skeleton, which, as shown here, we can actually load the ontology we're interested in using and have defined the namespaces that we're using. So RDFS, FOF, etc. Load our ontology and draw a tree of arrows between columns in the spreadsheet, relationships that we're interested in, and other columns. So here we take this generated column for the MusicBrainz IDs as the subject. We take the total sales that we produced by splitting and then multiplying the numbers as the object, and we attach to that arrow this total sales predicate. Okay? When we've done that, we can look down at the preview and see we get a lot of triples which are exactly of the form that we want. The Beatles total sales are this many as an integer. Okay. Another kind of data source that we might want to produce RDF from in order to make a linked data set are relational databases. And the W3C have come up with 2 specifications that will let us broadly follow this path, starting at a relational database, ending up with a queryable endpoint in Sparkle. Okay? Now, I say 2 means skipping over this bit in the middle, because this bit in the middle actually distinguishes quite well the 2 approaches. And the first one in this recommendation, W3C recommendation, is called the direct mapping. In the direct mapping, you just pick up your relational schema as it exists and turn it somehow into RDF. That doesn't let us align across vocabularies that are already known. It doesn't let us reconcile or align with instances that are already known. It just produces some sort of RDF data from our relational data. Okay? On the other hand, that R2RML, the relational to RDF mapping language, lets us build mappings that say, okay, we need to construct URIs according to a certain scheme. We need to use certain classes and properties in existing vocabularies to encode that data. Okay? Much more powerful, and that's actually the means, as you'll see in the examples, by which we turn the MusicBrainz relational database dump into RDF during Euclid. So, to follow that example, the MusicBrainz relational schema, quite a complex thing. We won't go into all the details, but you can look at them in our R2RML mappings. But there are entities that are recognizable at the top level. So artists, and artists have credits for works. We have what's called a release group, which is more or less what people think of as albums, just as I was describing earlier with Signal Group, as we'll see. We have releases. So at a certain point in space and time, we released within this release group the idea of an album. We have a medium on which that release was made. So was it released on CD or on vinyl or on cassette tape or DAT or any of these other things that have been there in the past? We have an associations to tracks through a track list, okay? And we have the abstract idea of a work, okay? That's what's in common between two cover versions. Completely separate tracks, but they're representations of the same work. Okay? On the artist level, you also have recording. This is what underlies a track. So the MusicOntology, now, previous slide was a relational database schema, or some part of it. This is an ontology that we want to re-express all of that information using in RDF. Okay? So this is the kind of mapping that we write using R2RML, and you can see that it's in Turtle. Every one of our mappings is going to be in a class called triples map. Okay? So we're mapping from something in the relational database into generated triples, generated RDF. Okay? Every triples map has 4 parts, okay, at the top level. Logical table, meaning, well, in the simplest case, does it just come from one table in the database, or does it come from something more complex? And then we have maps forming subjects and objects and the nomination of a predicate to link them. Okay? So in this case, we are encoding artists. So a logical table is just the artist table in MusicBrainz. We're going to put every instance, every row in that table, we're going to make it an instance of a class. Okay? So we explicitly say that there's a class associated with this subject map, which is music artist. Okay? So every row in the artist table turns into an instance of music artist in RDF. Okay? We don't stop there. Well, first we need to say, how do you turn the column in that row that somehow identifies it, usually the primary key, into a URI? Okay? So the rest of the subject map, the start of the triple, is a template that shows us how to make a URI for artists in MusicBrainz. Okay? And that says, you take the namespace, musicbrainz.org, you put /artist, and then you put the value of the GID, or the GUID column, that has this identifier with numbers and letters with hyphens in between. And on the end, we put the #_ that we mentioned at the end. Okay? Because we're really making non-document identifiers. When this rule picks up from the artist table, okay, the column that has the GUID for Beatles, it's going to construct a URI, the one that we've been using throughout, with a #_ in the end. That means we're really making a statement in this triple about the Beatles. Okay? The first thing you get from this rule is the Beatles are a music artist. They go in the class. But then out of this rule, we get a second triple, which says, in the predicate object map, here's the predicate we want to use, which is from the MusicOntology, a link to the plain GUID. Okay? And as the object, we just use the value from the GUID column that's also used in the URI, okay? But we treat it as a literal, and we give it the data type XSD string. Okay? So for every row in this table that the rule hits, we get 2 triples. We get the ID encoded as a URI with the membership of the music artist class, and we get that same URI associated with the simple GUID predicate relationship with the plain GUID as a literal. Okay? Next one, slightly more complex. Okay? Same form, we have a triples map, and it has a logical table, and it has the subject map, the predicate, and an object map. Okay? This time, the logical table isn't just a simple table from the database. Instead, it's a SQL query. Okay? Looks a lot like Sparkle, but this one's SQL. Okay? One easy way to tell that is, instead of just joining things implicitly through a graph pattern, which is what Sparkle does, SQL explicitly says we have an inner join. Okay? So we're joining 2 tables in the relational database, artist and artist name, according to a condition. Okay? So the artist defines its primary name in a table, in a join table full of names. Some artists actually have multiple names. They have aliases, which you can see in the full set of mappings. Okay? So the basis of the map is to first do a SQL query that makes a logical table, and then we're going to go through that table and turn rows into triples. How do we do it? Well, just as before, the subject map doesn't put things in classes. In fact, in this case, they would already be in classes because it's an inner join on the artist table. And the last rule turned everyone in the artist table into, in RDF, a member of the music artist class. So we don't need a class. Instead, we just say, let's make the subject the same way with the template. Okay? So every ID is going to become musicbrainz.org/artist/ID #_. The predicate that we use for the triple is fauve name, which we've encountered several times. Okay? And then the object just pulls the name column as a literal from the database. Okay? So the query puts together the query puts together the artist table and the artist name table, and then we query over the top and say, okay, for every artist ID, put it together with the name from the other table and use fauve name to make that relationship in RDF. Okay, now a quick word about advanced relations, but there's a much longer presentation about this mapping which will be recorded and made available by Euclid. Okay? What the next generation schema from MusicBrainz would like to do is to, without changing their schema, okay, which one normally has to do with relational databases, allow new relationships to be asserted between things, between entities in MusicBrainz. So I want to say, pick either two artists, or an artist and an album, or an artist and their label, and say that there's a new type of relationship that can hold between them. This is what RDF is very, very good at, and it's what relational databases make quite difficult. Okay? Within constraints, which are its only entities that already exist and have been paired, okay, this part of the schema allows you to introduce new links between pairs of those things. Just to give you an idea how complex that gets, in order just to find band membership, which is an advanced relationship, we need this SQL query that has 4 inner joins between different tables. But what we produce in RDF, you can see in the subject predicate object map, we've got the same subject as before, make an artist ID into an artist URI, use the predicate member of from the MusicOntology, and then also use a template to make the band into an artist URI. So we make one triple. For instance, Paul McCartney, member of the Beatles, out of this very difficult SQL query. Okay? If you look at the longer presentation, you'll also see you need all of these joins, between 4 joins, 5 tables, in order to get DBpedia IDs for things. So whereas in Sparkle, we can ask, is DBpedia's ID for Paul McCartney a member of DBpedia's The Beatles with one triple pattern? Okay? If we do that over the SQL database, we need 12 joins and a lot of writing and renaming of tables to get that to work. In any case, the mapping is done for you, so you get the SQL interface and hopefully, the Sparkle interface, and I've already tried some of those Sparkle queries in Module 2. If not, please take a look at the exercises site right now. Okay, another potential source of linked data is from text, from narrative text. There are tools such as OpenCalais, which will use linked data encoded knowledge to look through text and especially to do entity recognition. You see, all of the underlines here are, that's a person we seem to know. That's a person we seem to know. Okay? In fact, I think all of these are people. No, there are some bands too. Okay? So, uses background knowledge such as DBpedia to find out what's represented in there for things of certain classes. And we have found some artists as people and some bands just using OpenCalais. OpenCalais, on the other hand, is kind of oriented towards news and doesn't have that good coverage, that good recall or precision over this text. Okay? Its poor recall means it will miss things, and its poor precision means that it might misidentify things. The same can be said for DBpedia Spotlight, which is just built on top of DBpedia. Okay? So you throw in some text, and it will come back and say, among that text are things that one can find in DBpedia. So here we've got a person and a musical genre, okay? But lots of things that have been missed or misidentified as well. Samantha does very well as it goes, is another alternative with a lot of data and a lot of disambiguation technology in the back end, but is similarly generic. If you want to extend it to a particular domain, you will struggle somewhat. An alternative to that is to build this kind of service or this kind of API yourself. And one place that you might look to do that is picking up the open source framework called Gate, the General Architecture for Text Engineering. Since the mid-90s, this has had a strong developer community, has kept under ongoing development, and has a number of high-profile commercial clients. Using Gate as a service, you can, for instance, go to Lottie, to an exposure of Gate as a service, which has learned not just from a DBpedia backend, but has gone back through Wikipedia and used the link texts. So the point at which you make a link to a specific resource or a specific page in Wikipedia, the text that was surrounded by the link to help better with synonyms and disambiguation when those bits of text are found in your larger text. So if we run some text, some music-related text about Justin Timberlake here, you'll see it accurately identifies and links Justin Timberlake. It accurately reflects the album, but it misses some albums, and it gets one wrong because that album name is shared with an album from another artist. Okay? So again, when you use these generic tools, usually trained over Wikipedia or DBpedia, you get often a free service or a freemium service, but you play a game with precision and recall. Sometimes you can get the characteristics you want by combining them. So DBpedia Spotlight across different categories of things, so people, location, and organizations, can do quite well sometimes. Precision on people is very high, but overall we get down to very low scores. Samantha does significantly better. Lodi is the only one to do very well on the recall side, but then if we use combinations of those two together, we get better than any individual tool. Okay? But we're still dealing with mainly generic tools. The best results we can get are from training text extraction using our specific data set and using our knowledge about how to disambiguate within that domain. So using Gate, using the open source platform and the MusicBrainz data set as provided in RDF by Euclid, you can train up the central part of this, entity recognition, which is a gazetteer, okay, a dictionary of identifiers for the entities of concern, and for us this would be music artists and their releases. You can build yourself a Sparkle query that finds those. So in particular, in the Sparkle query, I'm looking for the label of the thing, the text that might be found, the instance URI, so the URI that I want to tag with, and the class that it belongs to. So is this an album, is it a solo artist, or is it a music group? Okay. So underneath that is a query that you can just go run against the Euclid MusicBrainz endpoint. If you run that query within gazetteer construction for the large knowledge base gazetteer in Gate, you can build a gazetteer that will go through text and be more accurate than any of those open services. What you might want to do if you want that available as a service but don't want to run the desktop version yourself, don't want to acquire the hardware for it, is put it up on the cloud so it runs as a service just like Spotlight and Samantha. Okay. So you can take the pipeline that you construct around this knowledge-based gazetteer constructed from your data set of interest and upload it to Gate Cloud. And they'll sort out the Amazon hosting so you can just access it as a service. Okay, the last tool that we want to talk about in the last, I think we have just over 10 minutes, concerns interlinking of data. So you can acquire your data from many different sources, from spreadsheets, from relational databases, from text. Before you publish your data, you want to make sure it's as interlinked as can be with everybody else's data. Okay? That makes it more comprehensible and more usable. So we go back to the middle example of turning MusicBrainz from a relational database into RDF and ask, can we do better about aligning the instances that we produce with other people's data sets, in particular with DBpedia. So we're looking at interlinking. We're going to use this open source tool called Silk, and in particular we'll need some familiarity with what's called the link specification language in Silk that defines rules from which the machine can decide how confident is it on the link between different entities. You can deploy Silk in various ways. Again, you can run it on a single machine if you've got a beefy machine. If you happen to have an Hadoop cluster, it will run over that. Or you can do a clustered server installation. All of them are available from the public download for Silk. The workflow is about identifying, first finding the data sets you're interested in. So for us, with MusicBrainz in hand, we identify that DBpedia is our target. Then we specify which parts of those data sets we're looking for interlinkage on. We write these rules in the specification language, and then we generate the links, okay, which then you can publish as link sets together with your data set. So in order to specify those, we need to know about RDF paths, okay? We're not just saying match A with B, we're saying look at the label of A and look at the FOF name associated with B in the other data set and compare those things, for instance. Before we compare them, we might want to do some transformation, okay? So commonly, you might want to reduce all of these texts that you have associated to resources down into lowercase, so you don't get mismatches due to capitalization. Then you want to specify comparators, okay? Do you just want an exact string match, or is a substring match okay? Or do you want something more flexible, like if it's text, a Levenstein edit distance, okay? How much editing would it take to change one into another? It's a good way to account for typos. If a single character is wrong, the edit distance is low. Okay. Other data types also have comparators we could do. So if we want to compare two albums and we want to look at their release date, there's things that we might want to transform and then compare in the release date to add evidence to this identification we're trying to make. And then finally, we might want to do some aggregative stuff, like we saw in Module 2 on Sparkle. If you want to count how many tracks are on both of these things that look like the same album, to add evidence to them being the same album. So, provided is a workbench with a graphical editor to drag and drop these data sets and to create rules, including with some external hookups to actually learn rules rather than specify them by hand. Looks as follows, gives you nicely a few statistics on the data sets that you're dealing with. So we've loaded DBpedia, loaded MusicBrainz, we're creating some same-as links between them, and this is the output that we're going to produce. So we can set all of the parameters to get those in and take them out, and then use the graphical editor to create a rule that says, look at the FOF name over MusicBrainz, look at the RDFS label over DBpedia, transform them both to lowercase so we don't get any mismatches based on capitalization, and then look at this Levenstein edit distance. Okay? So if you start with 1, how many essentially keyboard presses would you have to make it minimally to make it into the other one? Okay, and then we can generate links, and each of these links between MusicBrainz IDs and DBpedia IDs, for once the Beatles doesn't appear, but here's AC/DC's potential link to a MusicBrainz ID. Each one of them has a confidence score. Okay, so if the edit distance was larger, the confidence goes down. If we can add evidence, we can boost some of those weights, like the track count. Here's the interface for learning rules, which we won't cover in detail, but again, as usual with Euclid, there will be screencasts for these tools. So please do come back and check the Vimeo channels to see, for instance, how that OpenRefine of the music sales data was done. I believe that's available right now. And coming up very soon, how the R2RML mapping is executed over MusicBrainz to make RDF, and our example of how to use Silk to make the alignment between MusicBrainz and DBpedia. I hope this session's been useful. We're ending on time. If you have any comments, please primarily make those via Twitter on our tweet channel, Euclid_projects. Please know that as we go through this material, we're producing very nice ebook. So especially if you're reading on a tablet platform, the text of what we do, the video, the little screencast demos, the exercises, the multiple choice channels are woven into a very rich channel via ebook. All of the material is available, less well woven together in an HTML, in a browser-based interface. All of our output as screencasts and webinars is available on the Vimeo channel, and the slides that you've just seen and all of them coming up are available on SlideShare. So we look forward very much to interacting with you on this material, and I hope this module was useful.